Chapter 10, Section 2, the nature of volcanic eruptions. The primary factors that determine whether a volcano erupts explosively or quietly include the characteristics or the makeup of the magma and the amount of dissolved gases in the magma. Viscosity is what we use to describe the characteristics of the magma, and viscosity just means the substance resistance to flow. Temperature influences a substance's viscosity, whether you're talking about water or motor oil. The warmer something is, such as the warmer magma, is going to have a lower viscosity. Cooler magma, though, has a higher viscosity. So remember, we're talking about the tendency to resist flowing. The composition of the magma, whether it's high silica or low silica, also influences that viscosity. So if it's a high silica, it has a high viscosity, like the rhyolitic lava. So a high viscosity means that it is very resistant to flow. So think about trying to pour molasses or peanut butter. A lower viscosity would have low silica. It's going to be more fluid, like a basaltic lava. So it's going to flow much easier like water. The composition of the magma, when we describe it, we can say that it's either basaltic, andesitic, or rhyolitic. If it's basaltic, it's roughly 50% silica, it is the least viscous, and it flows 30 to 60 kilometers per hour. That's very fast. An andesitic magma is going to have roughly 60% silica, a medium viscosity, and it will flow 10 kilometers per hour. Rhyolitic lava, or magma, would have 70% silica. It's going to be the most viscous, and it'll only flow 1 kilometer per hour. You could generally outrun that. A vent is an opening to the Earth's surface. During explosions, the trapped gases will push the magma out. The violence of the eruption is related to how easily those gases can escape the magma. Gases escape easily from a very fluid magma, and a very viscous magma, a thick, chunky magma, is going to produce a more violent eruption because it allows those trapped gases to pile up and build up, and then when they do explode, we have larger chunks of rock and block that goes flying through the air, so it appears more violent. Depending on the type of eruption, volcanoes can produce lava flows or eject pyroclastics, or both. A pyroclastic is just anything that is ejected from a volcano. All eruptions, no matter what kind they are, will emit large amounts of gas. Most of that is going to be water vapor and carbon dioxide. Here in your textbook you have a table that summarizes the silica content and viscosity, the gas content. So a basaltic magma will have the least amount of gas, whereas a rhyolitic will have the most, which makes sense because remember the basaltic is very thin and fluid, whereas the rhyolitic is the thick, chunky, peanut butter-like. The tendency to form pyroclastics or ejected rock fragments. The basaltic, which remember is the fluid, runny stuff, probably not going to eject a pyroclastic, whereas the thick rhyolitic lava is more likely to. These are just the volcanic landforms that form from each of these types of magma. Pyroclastic material are just particles from the volcanic eruptions. These fragments can range in size anywhere from fine dust all the way up to boulders or fire fragments. Tephra is a term, it's Greek and it means ash, is a generic term for any airborne pyroclastic accumulation. Ash, to be considered ash, is going to be very fine grain, less than 2 millimeters, generally dominated by broken glass shards, but it also has variable amounts of broken crystal and rock fragment included in it. Lapilli are fragments anywhere from 2 to 64 millimeters in size. Blocks are larger than 64 millimeters or 6.4 centimeters, and those are ejected in a solid state. Bombs would be ejected blobs of hot lava streamlined in flight. These are going to be anything larger than 64 millimeters in diameter. Here we have the types of volcanoes. There's a flood or plateau basalt. Not really what we think of when we think of a volcano, but this is a very liquid lava flow. It's very widespread and it emits fractures. Shield volcanoes, cinder cones, and composite or stratovolcanoes, those are the more common types of volcanoes that we're used to seeing. A volcanic dome forms from a very viscous lava. They can be very small and explosive, and they can occur adjacent to craters of composite volcanoes. Mount St. Helens is an example of a lava dome. And then the calderas are very large composite volcanoes that collapse after an explosive period. So the first type of volcano that we're really going to look at is a cinder cone. A cinder cone is the simplest type of volcano. They're built from particles and blobs of congealed lava that are ejected from a single vent. Most generally, this is what you see like on the moon's surface when we look at pictures of that. They're not going to be very stable, and they're not going to be very large. Next, we have a composite or stratovolcano. Some of the Earth's grandest mountains are composite volcanoes, sometimes called stratovolcanoes. They are typically steep-sided. They are symmetrical cones of large dimension built of alternating layers of lava flows, of volcanic ash, cinders, blocks, and bombs, and they can rise as much as 8,000 feet above their bases. Examples include Mount Fuji in Japan, Mount Shasta, as we can see here in California, Mount Hood in Oregon, and Mount St. Helens and Mount Rainier in Washington. Here's the picture of Mount St. Helens, the before and after shots. A shield volcano. Shield volcanoes are a little bit different. They contrast with those stratovolcanoes both in origin and morphology. Their name comes from the low angle profile, which resembles the personal shields that were carried by warriors. They're formed primarily by the successive accumulation of fluid lava flows, which come from the summit or flank fissures. So it leaks out the side, or it comes out the top. This is going to be a very fluid, liquid type lava that's just going to come up and flow out, whereas these are built by chunks and chunks and chunks, exploding and then layering, exploding and then layering. Other types of volcanic landforms, like this flood or plateau basalt, or a lava plateau, high volume eruptions that flood vast areas of the earth, covering broad regions with flat-lying lava surfaces. These are said to be the result of mantle convection through hotspots. They can occur sporadically in time and place. In the U.S., we're familiar with the Columbia River flood basalts, which represent hundreds of black basalt lava layers, and they cover eastern Washington, parts of Idaho, and Oregon. This is what those would look like, that basaltic type rock. They look almost like layer cakes on the Earth's surface. A volcanic dome forms when you have a slow eruption of very thick lava or multiple eruptions of different kinds of lava. Instead of breaking through to the surface, the material builds up under the ground, causing the huge lava dome mound to form, and it continually pushes it and pushes it and pushes it. So there's gas and heat escaping from the outside, but there's not enough pressure to push that large chunk of whatever that buildup is. So it's almost like a lid on a pot. Then we have a caldera, and it's just a large cauldron-like hollow that forms shortly after the emptying of the magma chamber in a volcanic eruption. When a large volume of magma is erupted over a short time, the structural support for the rock surrounding it is going to be lost, and it becomes unstable, and so it will actually collapse in on itself. And that creates these large holes. Oftentimes they fill in with water, and they make some pretty neat scenery. So volcanic hazards. Hazards can include lava flows, mud flows, volcanic ash, and pyroclastic flows. Here you can see lava that's pouring steadily from a volcano in Hawaii. As it hits the ocean, it's creating that giant steam wall. Don't know that I would sit necessarily right there in the water, but that's okay. Some other lava flows in Pahoa, you can see how slow that is. It's a very slow flowing, very viscous solution. Skip ahead a little bit. You can see how slow that's moving. So even though you have time to evacuate and maybe put up some, like here they put up some gravel and rock and dirt to protect that power pole, you have time to do those types of things to prevent the hazards that come along with lava, but pretty much where the lava wants to go, it's going to go. And everything in its path is going to be destroyed, whether it's a roadway or a building. And you can see there it burnt through that fence. It took down that shed. There's not much else you can do when you're dealing with a lava flow. This one's kind of neat. I don't have the sound turned up, but it's going through an orchard, a nut orchard, and you can hear the nuts popping, and the roots on the trees are popping. So it's burning up the trees, but it's also destroying the root system below. So we have complete destruction of the Earth's surface right here. So we've got to start over, pioneer species, the whole ecological succession. And then finally, in Iceland, they flew a drone over this lake of fire. You can see how quickly that lava is moving. It's also cooling very quickly too because of the cold temperatures. So up until recently, technology hasn't been able to get that close. They've developed cameras and equipment that can withstand those sharp temperature increases as they fly over. So that's kind of neat that we get to see these things that we've never been able to see before. And then finally we have a lahar, which occurs when water-soaked volcanic ash and rock will slide rapidly downhill. So it's almost like a mud flow, but it's really volcanic ash and water. In places where there's not a lot of green stuff, there's not a lot of grass to slow it down, there's not trees, a flash flood of any kind, or a mud flow like this, can be very destructive and very, very dangerous. Then we have this New Zealand volcano. This happened December 9th, 2019. There were people on a boat nearby, and they actually caught it. They realized what was going on. They start getting scared. They're watching the active volcano. They're trying to get away from it. There's only so much they can do. And then there's another view. You can see the smoke and the ash. And then a local research institute happened to have a camera on it, and it's kind of like a time lapse. You can see the plume of ash and steam rising from the crater as this occurs. And the scariest part of all were these tourists that happened to be on the island. And luckily they made it out in time.